Hello everyone, my name is Minkyu Park in Virtual Lab in charge of Chief Scientific Officers. Today I'm going to explain for questions and answer in Phonon webinar, and I want to say some tips for the Phonon calculations. So today I'm gonna be start from the questions and answers in the Phonon webinar and some tips for the Phonon calculations. So there are many questions in the Phonon webinar, but I select one or two and then gonna be answering for that. First issue is the negative mode, which is same meaning of the imaginary mode in Phonon calculations. And some guy asked for the problem with a Husler alloy. This system is consists of palladium and yttrium and tin. He get a negative frequency mode in here, and he tried the calculation with quantum espressos. Because of the negative frequency mode, he cannot calculate the phonon coupling coefficient. So he tried many things, and then he tried 5 years, but he finally cannot get any results for that. So I want to help for these questions. So phonon negative mode or imaginary mode is very important some part of the scientific research because they in the imaginary modes reflect the structural instability. So I want to explain first for this one, harmonic approximation. In the harmonic approximation is a crystal potential energy derivative of the atomic displacement will be zero in the harmonic approximations at equilibrium. You can see here, for example, this is for this very famous paper in 2015. I think this is tin. Alpha tin and omega tin is it has been known that very stable structures. However, but beta phase BCC structure is very unstable. So when you calculate the alpha, beta, and omega phase by using Phonon calculations, you can get any negative mode in the alpha and omega case. However, you can get a negative mode in BCC is beta phase in the P point and N point, which means this is very unstable, which means the same meaning of the structural instability. And also this is also, it does not make sense because omega square cannot be the under zeros. So practically and in my experience, the problem is the structure is not fully conversed, or this is basically not stable. It's unstable structures, which means when you finish the calculation and you can see the atomic forces, force x and as a function of x and y and z directions, you can see this structure of force, atomic force cannot be zero. I'm gonna be explain next page. Or the atoms are not located in the equilibrium positions. I'm gonna explain more details. You may check the atomic force in your output file in the materials care. When you go the JavaScript file, you can see these kind of things, atomic forces. So you can see here, basically is fully conversed structures will be almost zero. You can see first type is not zero, not zero, not zero. But usually type 4 is the almost zero. This is exactly zero. So this is well conversed. But other atoms in the system is not conversed fully. So in this case, you can see this kind of negatives value. And also you cannot calculate the electron phonon coefficient or something other properties related on the phonons. So you should very carefully check for your structure is fully conversed. So second issue is the dielectric constant and electron phonon coefficient calculations. So as you know, the dielectric concept and definition of dielectric constant is only defined in the non-metal system because the dielectric constant cannot be defined in the metallic system. So in the quantum espresso, you can use the epsilon equal true tag. You can, when you calculate the dielectric constant, when you finish to calculate the dielectric constant successfully, you can see this kind of matrix. So you can usually in the isotopically equivalent system is a diagonalized component will be almost same. In this case is the silicon case. Silicon is known that the dielectric constants around 11 or 10 or 11. So it's not bad for the calculation. And also you can calculate the result of the effective charges calculation in here, in the first atom and second atom. Because of the silicon is consists of two atoms in the unit cell, so you can see the two components of the effective charge. Okay, next case is the electron phonon coefficient calculation. It is also defined in the metallic system. When you want to calculate the electron phonon coefficient, you can turn on the electron phonon on tag. This is the consists of simple and interpolated lambda tetra and gamma tetra. So you can only calculate the metallic system. So I want to explain and make sure that when you calculate the phonons, you should check for the convergence. I mentioned before, atomic force or the SCF convergence, you should check very carefully. And also think about what is your system. Is metal or semiconductor or insulator? And I want to some explanation for our input file in the phonon calculations. When you start for the calculation, you should perform the VC relax because the structure I mentioned previously, your structure should be very, very, very accurate and very, very high accuracy calculation, and you need the ground state structure. So when you start for the phonon calculation, you start from the relax or VC relax. But I recommend VC-Lex. But VC-Lex is not 100% guarantee your structure is the ground state. So some case you should manually calculate by using the lattice constant or relative positions. And next to the first threshold in the quantum espresso, there are force converse threshold is tag. This is the tag in the quantum espresso. And please make sure that use the smaller value in the ordinary calculation because the phonon is very sensitive calculation. In the finite difference method, for example, is that on displaced and displacement atoms are only different from 0.01 angstrom. So you should very careful use the force convergence threshold parameters. Recommended value is 1.0 times to the -5. This unit is our Rydberg per Bohr. And next case is cutoff energy and cutoff rho. This large value is mandatory because for the accurate calculation, this is the kinetic energy cutoff and the wave functions. And recommended value is E cut low. It's going to be 8 to 12 times for the E cut. So in the material scale, there are some maybe 8 times for the E cut times 8, gonna be E cut rho. So if you want to expand more, and you can change it 12 or something. When you calculate the two-dimensional system, you should careful for the self vector with the VC relax. Self vector is the how to change your cell compared with the previous calculation. I mean the first initial coordination. So I recommend the self vector 2 for the low dimensional. And electron convergence threshold, this is almost the same concept of force threshold, but this is for the SCF calculation. So I recommend lower than, at least more than 1.0 -9, like -10 or -12, something like that. I recommend anyway, this is the minimum value in the phonon calculations. And last part is the K-point grid mesh. Actually, this is depending on the cell, but remember, at least you can make 30. Make 30 is the minimum requirement. So what is make 30? For example, your cell vector is going to be 5, 5, and 10 angstrom, and you should be set up the Kx. You should make 30. For the Kx is the 5 times 6, gonna be 30, right? So your A1 vector is 5. at least you can use larger than 6, okay, in the Phonon calculation. So what if A3 vector gonna be 10 angstrom? So you should make 30, right? So you can use the 3 for n-list K point. So this concept is gonna be very useful for the Phonon calculation. And also any further question, please contact Material Square anytime. We are welcome for the questions of phonon or electron or molecular dynamics kind of a call. All right, thank you for that. Bye-bye.